So today we're going to look at shear flow in a closed section. So here we have a rectangular section with a shear force applied, and from the previous class you would recognise this set of equations here, where if we're trying to calculate shear flow in the section, this term, then it's dependent on the applied shear force, which we know, thickness of the section, which we know, the IXX, which you know how to calculate now, the geometry of the section, which is in here, and there's the constant shear flow, which wasn't a problem for open sections because we could start the integration at a free edge. But with our closed section we have no free edge, so we need a way of calculating this constant shear flow. So everything in this big term here we're going to call QB, and that stands for basic shear flow. And we'll use this basic shear flow to then at the end calculate the constant shear flow. And once we have the constant shear flow and the basic shear flow, we'll add them together to work out the real shear flow in the section. To find the constant shear flow, we have to use moment equilibrium in the section. So if we look at our section over here on the right, we have some externally applied load here and some internal shear forces that are set up, or some internal shear flows. Now, based on the principle of equilibrium, we can say that the external shear flows or the internal shear flows are on the same cut. The moment of those two should be the same. So I'll just give you a little bit more definition here. The magnitude of this shear force we'll call SY, and the distance from the axis we'll call psi. And you'll notice that if we take this reference point here, the shear force is having an anti-clockwise moment about that reference point. If we look at the same reference point in the section, then we need to take our moments in an anti-clockwise direction. So if we do that, we can say up here that the moments in anti-clockwise is positive are the external moments are shear force times the distance, and the internal moments are the integral around the loop of PQ ds, where Q is our total shear flow that we're trying to calculate, ds is the length of a little element of section, and P is the moment arm to that piece of section. And you should be familiar with this from the lectures. We can break the Q into two parts, as we did on the previous slide, and we can break it into QB and QS naught. And we know that this QS naught is constant around the entire section. So we can take that outside the integral, whereas QB is not constant. We need to keep that inside. So if we also know from geometry in class that this integral here, PQds, is also related to the cross-sectional area of the section, or the total enclosed area in the section, and that is given here. So at the end, once we've equilibrated moments, if we equate moments in such a way that we take the moments about the point in line with the shear force, if we take that as our reference point, then this can go to 0. And we can end up with that QS naught equals the integral around the loop P QB ds on 2a, and in this case we also need a minus sign because of the way we've defined our moments. Okay, so how do we find QS naught? Well, to find QS naught we have to break into the section somewhere. And we can't find either QSB or QS naught without starting our integration somewhere. So what we do is we take a cut, so in this case we're going to make a cut here. Usually it says down here, usually the cut will be at the intersection of the applied force and the neutral axis, or the applied force and the section. So we would usually take the cut somewhere up here, but today I'll show you a general case. So say we cut there. We can then go about calculating the QBs around the section, and if you've done enough of these examples, you'll know that the basic shear flows will look something like this. Okay, but that's as if we'd made an open section, and we don't have an open section here. We've got a closed section. So what we've got to do is find our QS naught. So if we go back to a previous slide, our QS naught here will modify the Q in every panel by that value. So that'll be constant around the section. So that will look something like this. Note that it's constant around the section. Now, if we add those two together to find our Q, it will look something like what we have here. Okay. So our cut location is here, and we have positive shear flows until we get to the centre of the body, and then they start going in the opposite direction to our path of integration, so then they become negative, and we go round and come back to zero again, and then back up to our cut section. And note that the shape is symmetric and the magnitudes about the neutral axis are also symmetric.